In this video, we drill down on electromagnetic induction and ask what's really pushing charges around when we see an induced EMF. And the answer is that we get a whole new species of electric field that turns out to be non-conservative, and this guy is called the induced electric field. So let's consider this simple experiment. A loop of wire surrounds a solenoid and the current is increasing in the solenoid. So this solenoid is producing a leftward magnetic field in its interior, and that field strength is increasing, which in turn means the loop is capturing an increasing leftward magnetic flux. Now Lenz's law tells us that the loop is going to respond with an induced current in the direction that opposes the flux change. So there's the induced magnetic field caused by the loop, and there's the direction of the induced current that's going to give us that rightward pointing magnetic field. And then Faraday's law tells us how to compute the induced EMF for this loop, which we'll get to in a second. But the point of this video is to explore what's actually pushing charges around in that loop. Well, it can't be magnetic field, since the magnetic field is zero outside of this long solenoid. And that means it must be an electric field at the location of the loop. But this induced electric field is different than any electric field we've seen before in our study of electrostatics. The big difference here is that it can't have a radial component given the symmetry of the problem, since Gauss's law would then imply we have a net charge hanging around on the solenoid if the electric flux integral is non-zero. But of course there's no net charge hanging around on this solenoid. And by symmetry, the electric field at the location of the loop can't have any axial component either. In other words, there's no asymmetry to give the field any left or right component. And all of this means that our induced electric field must actually be circumferential or curling. And this makes a lot of sense when we see current swirling in that loop. And it's not too hard to calculate the magnitude of this curling electric field. All we're going to do is compare two different calculations of the magnitude of the EMF in that loop. So first we'll use Faraday's law, which tells us the magnitude of this EMF is just given by the absolute value of the rate of change in the magnetic flux captured by that loop. Then we'll compute the EMF by integrating electric field around the entire loop in the direction of E. And if you're rusty on these integrals, I'll post a link to my electrostatic potential integrals up at the top. So the EMF around this entire loop is given by integrating electric field dotted into length increment, but the field is circumferential, making it parallel to the length increment at every point. So the dot product is trivial here, and we just get the integral of E times dl around the loop. But by symmetry, E has a constant magnitude along the loop as well, and this means we can factor it out of the integral. Now all that's left to do is integrate dl over the entire loop, and that just gives us the circumference 2 pi r. And equating our two calculations of EMF, we can write down the magnitude of the induced electric field, and that's given by the absolute value of the rate of change in the magnetic flux up there in the numerator, then divided by 2 pi r. Again, that's the circumference of a loop of radius r centered on this solenoid. So we see that a changing magnetic flux induces an electric field, and in practice, this is how we're going to calculate induced electric fields in a practical context. Now, if we generalize to include signs in this calculation, all we've really done is restate Faraday's law with the EMF computed as a path integral of electric field. So this says the path integral of electric field around a closed loop is equal to the negative of the rate of change in magnetic flux. And that's how we'll express Faraday's law when we're summarizing Maxwell's equations in integral form. Now, before we get to our numeric example, there's one final point to make about this induced electric field. It's non-conservative. Remember, a key point about conservative forces is that the work they do is path independent, but this is equivalent to saying the work they do on a closed loop is zero. Well, that's the opposite of what we're seeing here, where the electric field is doing non-zero work per unit charge around the complete loop, and that's what the EMF is measuring here. So when we need to distinguish between our ordinary conservative electrostatic electric field and this new non-conservative induced electric field, we'll label the induced electric field as E with a subscript of NC for non-conservative. So let's compute the induced electric field magnitude for a solenoid surrounded by a loop. In this example, we're told we have a solenoid with 10,000 turns per meter and a cross-sectional area of 5 centimeters squared, and is carrying a current that's increasing at a rate of 2 amps per second. Now remember, without seeing changes in current here, we aren't going to see any induction effects. So it's the rate of change in that current that matters. Now this solenoid is surrounded by a conductive loop of diameter 4 centimeters, and that's aligned coaxially as shown in the diagram. And I didn't write it in the example, but we're only interested in magnitudes for this example. So we just want the magnitude of the induced EMF and the magnitude of the induced electric field. And that means we're just going to ignore minus signs instead of laboriously showing absolute value bars all over the place. So in part A, we're trying to find the induced EMF in the loop, and we're just quoting Faraday's law here, but again, I'm going to ignore minus signs. So stated as a magnitude, the induced EMF is just the rate of change in the magnetic flux. Now we have to express that magnetic flux in terms of the details of the problem. So I'm going to pull the time derivative out in front. And then the magnetic flux captured by this loop is only happening over the cross-section of the solenoid. That's the only place there's a magnetic field. So be very careful to use that for your cross-sectional area, not the area of the loop itself, just the area that has magnetic field through it. So our magnetic flux calculation is simply going to be A times B, where A is the cross-sectional area of the solenoid. So next we can put in the details about the solenoid magnetic field. And remember, a solenoid magnetic field is given by mu naught times little n times I, where that little n is the turns per unit length. Now there's only one variable in here that has time dependence, and that's the I, so everything else can be factored out in front as a constant. And this leaves us with mu naught times A times little n times di dt. Now subbing in the numbers, mu naught, that's the permeability of free space, that's 4 pi times 10 to the negative 7. I'm just going to leave the units off to save space here. And then our cross-sectional area, this is tricky because we have to convert this to square meters, but we're given square centimeters. So remember, when you're doing the unit analysis on this, we have to apply 2 factors of 1 over 100 to cancel both of those factors of centimeters. In other words, to convert to square meters, I need to shift the decimal place 4 times. So I end up with 0.005 square meters for that cross-sectional area. We were told the little n, the turns per unit length, is 10,000. And finally, we were told the rate of change in the current is 2 amps per second. So we'll put a 2 in there. And to 3 significant digits, I get 1.26 times 10 to the negative 5th volts. And it might be more natural to express that as 12.6 microvolts. Now for part B, we're trying to compute the induced electric field at the loop. And we've already discovered that, at least ignoring minus signs, this is just the rate of change in the magnetic flux captured by the loop, then divided by 2 pi times the radius of the loop. Well, all we did in part A was actually do that rate of change in the magnetic flux calculation. So we can just take that previous number, and that's 1.26 times 10 to the negative 5th volts, and then we're going to divide that by 2 pi times the radius of the loop. So that's a radius of 2 centimeters, but it has to be converted to meters. So I'm going to write that as 0.02. I'll leave the units on there. And when we run the numbers on this to 3 significant digits, we get 1.00 times 10 to the negative 4th volts per meter. In the next video, we continue our quest to complete Maxwell's equations in integral form by patching up Ampere's law with a new term called the displacement current. And we discover that a changing electric field can generate a magnetic field even when no conduction current is penetrating an Amperian loop. I'll put a link to that video at the upper left, and I'll see you there.